Hi, welcome back. In this lecture, I want to talk about how to integrate Numpy within Cython code. By the end of this lecture, we will be able to use Numpy in a Cython code using memory views. Before starting with the core of this lecture, I want just to give a quick recap about list arrays and Numpy. We saw that list objects have an overhead of each dereference and indirection, as the object they reference can occur anywhere in memory. This results in the so-called problem of memory fragmentation. Instead, if you're using Python array module or NumPy, array objects store primitive types in contiguous block of RAM, which enable faster addressing. So these are enabled by Python array module, by also NumPy. NumPy in particular allows multi-dimensional storage and a wider range of primitive types, including also complex number that we will need for our Julia set code. In this lecture, I focus on the NumPy and how to use NumPy within Cython code. In this lecture, I'm going to use the Julia set code in NumPy, and we're going to have a NumPy version of the Julia set code. So instead of having the arrays as a list, we can just declare as a NumPy matrices or arrays. One surprising thing it might be for you that when you run the NumPy Julia set code, it will be slower than the version using Python lists. Right? So that's quite strange. At the very least, we would expect similar performance than the Python list version. So we have this slowdown with respect to the Python list version because of the overhead of dereferencing individual elements in the NumPy arrays that is higher than the referencing time that we have in Python list version. So why is that? Well, NumPy was never really designed to be used within the loops, right? So when we work with NumPy, we always try to formulate our problem using arrays and vector operation. So NumPy is not designed for operation within the loops, and we should avoid, but in many cases we cannot avoid it if vectorization, the vector formulation is not so easy to obtain. So one reason to compile our code with NumPy is actually to optimize, so we can still keep our NumPy arrays within the loops, and then we use the compilation to remove this overhead coming from the referencing. Cython has two special syntax forms for embedding NumPy arrays within the Cython code. There are older versions of Cython that has a special access type for NumPy arrays. However, this is not really much in use anymore. More recently, Python and Cython added a so-called generalized buffer interface protocol through the memory view. So what is the memory view? Well, memory view is a way for us to allow us to have the same low-level access to any object that implements the buffer interface, including NumPy arrays and Python arrays. A kind of a big abstraction of different objects, might be NumPy arrays, Python arrays. In this buffer interface, blocks of memory can be easily shared with other C libraries without any need to convert them to Python object into another form. Right? So this is a very nice abstraction that allows us access from C interfaces, Python interfaces. Well, that's a very nice concept. So let's see how we do in practice, how we add NumPy within our Cython code. So the first thing we need to do is, of course, import NumPy, but also we need to import the Cython file. So we do import NumPy as MP. So that's the first step. And then the second step is to tell our function calculate_z that we are passing two NumPy arrays, double complex zs and double complex cs. So these are the NumPy arrays that we are giving through the arguments of this function using the so-called memory view annotation. So what is this memory annotation? Is actually the type, and then is the square brackets and then a column between the square brackets. So these two are basically the memory view of our arrays ZS and CS. Then we also provide, we also create the output as a NumPy array of the type, in this case type integer, and then we want to define as a Cython type. So we're going to use the cdef like we did before for annotating with the types, and then we add the memory view. So we say that this is an integer, and then we provide the square bracket column. So one thing here to notice that I've been using numpy.empty that has the function of creating an array called output, but not initializing. So it's not filling with the values. We actually don't care because this output array will be filled later on in this cycle here. So this the fact that we are creating but not initializing buys us some little bit time. So this will be slightly faster than creating and initializing to 0. When we want to use NumPy within our code, we also need to change slightly the setup.py for our Cythonized NumPy code. So the first thing we need to have this import in setup for NumPy. And other things also we need to tell where actually the NumPy modules are. So we add two pieces. So what is the performance of Cython NumPy? So the pure Python version has a overhead every time it differences a Python complex object, so that is very slow. But these differences occur in the outer loop, so don't account for much of the execution time when we used our part of the code that has been Cythonized. So if I use this Julia 1py, where I have NumPy arrays within our Cython function, we see that it takes roughly 0.330. This is pretty much the same performance that we obtained by Cythonizing with the types our code. So we saw that after using Cython with the NumPy, we go back to the C speed, right? So to the real speed that we want to use. So we didn't need to vectorize or to make in a vector formulation. We can keep the loops, and then we compile. We use this compilation approach using Cython. So to summarize, Cython allows us to use NumPy arrays with generalized buffer interface protocol that is introduced through the concepts of a memory view. To use the memory views, we use the bracket notation and the column within notation for memory for expressing memory view. And then still we will need to use the cdef for defining the NumPy data type. This is the last slides. Talk to you soon.